Welcome back. In this section, we'll be talking about another collection of sequences that have a similar property, and these are called geometric sequences. So when we were looking at arithmetic sequences in 13.2, those were sequences where one term minus a consecutive term, that would be a common difference, and that was what made something arithmetic. For geometric, instead of one term minus another, we're taking consecutive terms and dividing them, one divided by another. And if that turns out to be a constant, so if the term k divided by term k minus 1, if that's equal to a constant, some constant r, well then we'll call that constant r the common ratio. So in other words, these are sequences where instead of going up by addition or subtraction, we're going up or going down by multiplication. So this would be a sequence where, for example, you go up by multiplying each term by 5 or multiplying each term by a half. So if you're thinking about describing it recursively, then you can say, well, you've got your first term, whatever the first term is, and each term can be found by taking the previous term and multiplying it by whatever that common ratio is. So for example, if your common ratio is 5 and you start with 1, then the sequence will go from 1 to 1 times 5, which is 5. Then the next one will be times 5 again, or 25. Then times 5 again, 125, and so on. So we're going to do the same sorts of things that we did in section 13.2. We're going to introduce the idea of a geometric sequence. We're eventually going to start coming up with formulas for geometric sequences, just like we did for the arithmetic ones as well. So first off, just to see whether we've got a geometric sequence at all, the one thing that we notice, this is not arithmetic for sure, because if you're looking at the numbers 2, 10, 50, 250, and so on, and thought it was arithmetic, you would notice immediately that it couldn't be, because we go up by adding 8, then adding 40, then adding 200. This is definitely not arithmetic, because the amount that we're adding each time is not a constant. On the other hand, you might notice that you do go up by the same amount by multiplication, that 2, 10, 50, 250, and 1250, you go up by multiplying by 5 each time. 2 times 5 gives you 10, times 5 again gives you 50, times 5 again gives you 250, and times 5 again gives you 1250. So that means that the common ratio here is 5. So the common ratio is 5, and we know that the first term is 2. So if we wanted a recursive definition, then we'd say if you want term n, then you'll find that by taking the previous term, term n minus 1, and multiplying it by that common ratio of 5. All right, so we've got some sequences to show that are geometric. And again, I'm going to do the same sort of thing that I did in 13.2, which is I'm going to use the official definition of what does it mean for something to be geometric. Well, if it's geometric, we would have to have this property, that term k divided by term k minus 1 would have to give us some constant r. So that's what I'm going to check to see, do I get a constant r when I take term k divided by term k minus 1. So first I just need to figure out what is term k. Well, for this one it's 5 to the k. Term k minus 1, well that would be 5 to the k minus 1. And if I looked at term k divided by term k minus 1, that's 5 to the k over 5 to the k minus 1. Using your exponent rules, that simplifies to give you just 5. And so, yes, that is definitely a constant. So, hooray, we know that the common ratio is 5. And we can say that the first term, a1, should be 5 to the 1, which is also 5. So it starts with 5, and every time we go up by multiplying by 5. So the sequence would be 5, 25, 125, and so on. All right, B, we can see that this is going to be an alternating sequence because we have a negative number being raised to a power. So I know that when the power is an even number, we'll get something positive. When the power is an odd number, we'll get something negative. Anyhow, let's continue on first by showing it's geometric. Term k would be 3 times negative 5 to the k, and term k minus 1 would be 3 times negative 5 to the k minus 1. And if we looked at term k divided by term k minus 1, we would get 3 times negative 5 to the k over 3 times negative 5 to the k minus 1. And a bunch of stuff cancels. The 3's will cancel, and most of the minus 5's will cancel, leaving just negative 5. So this one, again, is also geometric. Geometric because we have a constant as that common ratio, so that ratio is negative 5. So each time we are multiplying by negative 5. And our first term, if we want to find what that is, that would be 3 times negative 5 to the 1, which is negative 15. So with this sequence, we begin with negative 15, and each time we multiply by negative 5. Okay, so now if we're looking at this terms of a geometric sequence, just like how we had for an arithmetic sequence, where if you knew for an arithmetic sequence the first term and the common difference, you could come up with a formula. And so same thing here, if we know our first term and our common ratio, then we can also come up with a formula. So term n is just found by taking our first term and multiplied by our common ratio to the power of n minus 1. And so not hard to do, really. Once we find our first term and our common ratio, then pretty much we automatically get our formula for an. So when we're looking at these, again, we first need to figure out that it's geometric. So first thing that you might do is just to see if you're looking at 1/5 minus a 10th, 2/5 minus 1/5, 4/5 minus 2/5. You confirm that these are not the same, so this is not arithmetic. If you did your subtractions, 1/5 minus a 10th is a 10th, 2/5 minus a 5th is a 5th, 4/5 minus 2/5 is 2/5. So not arithmetic. So now you check to see geometric. What about 1/5 divided by 1/10? What about 2/5 divided by 1/5? What about 4/5 divided by 2/5? And we'll see for all of those are all the same. That for all of these, they all have a common ratio of 2. That we go up by multiplying by 2 each time. So once we know that our first term is 1/10 and our common ratio is 2, then our formula for an is easy enough to find. It's just 1/10 multiplied by 2 to the power of n minus 1. So if you're looking for a10, the 10th term in the sequence, that would be 1/10 times 2 to the power of 9. And that gives you 512 over 10, which, if we simplify that, that's 256 over 5. All right, so this is like the other one that we had at the end of 13.2, sort of a troublesome one here. We have a geometric sequence, and we know some of the terms in the sequence. We know the 4th term, and we know the 7th term. And again, we want to come up with a formula for that geometric sequence. Again, because we don't have consecutive terms, if we had the 3rd term and the 4th term, it would be easy to figure out the common ratio. But because we have the 7th term and the 4th term, finding the common ratio is maybe a little bit less easy. But we'll do the same thing that we did with the similar problem in 13.2. If it's a geometric sequence, we know that an would be a times r to the n minus 1. And if we know that a4, the 4th term, is 54, then 54 should be a times r to the 4 minus 1, which is r to the power of 3. And since a7 is 2, then 2 should be a times r to the 7 minus 1, which is 6. So you've got 2 equations, 2 unknowns. And so I'm going to start off with, from equation 1, I could say that a is the same thing as 54 over r cubed. just by taking that first equation and solving for a. And then I'm going to substitute this into equation 2. So I'm going to replace the a with 54 over r cubed. And then things are going to simplify fairly nicely. R cubed and r to the 6 will cancel, leaving r cubed. So you'll have 2 equals 54r cubed. Or dividing both sides by 54, 1/27 is r cubed, which means that r is cube root of 1/27, which is 1/3. So there we go. We found what r is, and once we know what r is, we can use that to find what a is using the previous equation. Since a is 54 over r cubed, then a should be 54 over 1/3 cubed. And if you use your calculator for that, 1/3 cubed is 1/27. 54 divided by 1/27 turns out to be 1,458. And so now we can write our formula. We can say, good for us. Our formula for an is our first term, a, which is 1458, times r, which is 1/3 to the power of n minus 1. And again, the nice thing about this is you can check to see if you're correct, because if you have your formula, or what you think is your formula for an, then you can use that to ask yourself, if I put in 4 for n, do I get 54 as my term? If I put in 7 for n, do I get 2 for my term? And you can check to see that using this formula, this does give you the correct value for a4 as well as for a7. So you can feel fairly confident that, yes, you've got the correct formula for an.